And so we know a little bit about this already. Couple different methods. O3 H nu, O2 oxygen. The stars means they're highly energetic species on there with this. And the wavelength has to be less than 20 nanometers or something like that. We talked about. And so there's a mechanism in here called the um, Chapman mechanism. And we'll go over that. You'll have to know. It is this mechanism, O2 plus UVC yields 2 oxygen. Oxygen plus O2 yields O3. I think we already went over this. And then O3 plus UVB yields O2 plus O. And this is circular. We produce O2 plus O that can produce ozone, etc. on this. You can look at figure 1A in your book to see this. And so we have ozone produced in the stratosphere by UVC and ozone destroyed in stratosphere by UVB, which is very useful, prevents that radiation from hitting us. That's fine. So what we're real interested in is there's other mechanisms on there. And so there's things called catalyst. A catalyst is involved in the reaction but not consumed, which makes them different. Makes them very, no, I don't want to say useful, but makes them very harmful because they're used over and over. Okay, so we'll go through mechanism one. Mechanism one, some catalyst X, which we represent by X, and X can be a lot of different things. We'll give you an example later. Plus O3 yields XO plus O2. So it helps abstract the oxygen on there. And then XO plus oxygen yields X plus O2. And when we add these all up, these reactions add up, we get the X's cancel and the XO, and we catalyze this reaction right here. O3 plus O yields 2O2. Now this occurs naturally in this, but it's not unlikely. So for the reaction to occur, O3 plus O to occur naturally, you have about an 18 kilojoule per mole activation energy. Now, an activation energy is the energy you have to get it over to have it react. This is this energy barrier here. From here to here is called the activation energy, E sub A. And on this side, we have O3 plus O, and over here we have O2. Okay, when you add a catalyst, X, what happens, I should draw it up here, I'll draw it here, is it lowers this activation energy and makes the reaction happen easier. And so you get more of it being destroyed, okay, because we lower the activation energy. And that's what X does. And note that X is not used in the overall reaction, okay? In general, X is a free radical. For example, chlorine, perhaps, or NO. If you draw the Lewis dot structure, you have a lone electron on there for this. Okay, so chlorine lowers this to about 2 kilojoules per mole, that activation energy. So the normal activation energy for O3 plus O is approximately 18 kilojoules per mole, somewhere in there. Doesn't really matter. When you add O3 plus X to get OX plus O2, you get about 2 kilojoules per mole for various X's. For chlorine, X equal to chlorine, it's about 2 kilojoules per mole for the activation energy. So we've lowered that activation energy, and that makes it easier for this to happen. So that's mechanism one. And these are natural. Actually, let's give an example of mechanism one. Let's do NO2. NO2 plus O yields 2NO. NO2 is a natural part of the troposphere, which NO2 gets transported into the stratosphere where it's turned into nitric oxide. So the nitric oxide is our catalyst. NO reacts with ozone to yields NO2 plus O2. NO2 plus oxygen yields NO plus O2, and the overall mechanism is O3 plus O yields O2. This activation energy is about 10 kilojoules per mole. So it lowers it, the activation energy, but not a whole lot on there. Okay. There are other ones. For example, CH4 plus oxygen can give you OH plus CH3, and OH turns out to be a catalyst that you often see. Okay, those are naturally occurring catalysts. Another type of mechanism is mechanism two, and this is a reactive species, again, a radical of some sort. X plus O3 yields XO plus O2. Then we have a different X, we call it X prime. So this requires two different catalysts. It could be chlorine and bromine, or it could be chlorine and chlorine. It doesn't matter. Just there's two of them, but they don't have to be the same. That's all that means. O3 yields XO prime plus O2, then XO plus XO prime yields XOO X prime, which then yields X plus X prime plus O2. And when you add these reactions, you get some canceling going on here. X's cancel, the X primes cancel, the XO cancels, and the XO primes cancel. And this is gone right here. And so you end up with 2O3 yields 3O2. Very destructive type catalyst. So those are the three types of catalysts. Now, this is not good, but it's not bad. X tends to be, when it becomes bad, is we put X in as man-made catalyst. Now, what's the result of this? It's a little bit tricky because the ozone destruction means, and UV as C and B will penetrate farther into the atmosphere, specifically the stratosphere. Okay, and so all that happens then is, since it's penetrating farther, it reaches where there's more oxygen lower in the and so we produce O3 because we have more UV C and B at lower altitudes. Okay, so it's somewhat self-healing. You'll never get rid of all of it on there. That's that mechanism. Okay, stop there.